So it's a pleasure to welcome David Gosset, who's our colleague at Waterloo and also at PR. He is going to be talking about some work on version of tomography called shadow tomography. And I'll hand it over to you.
Thanks, Ashwin. And yeah, thanks for coming to my talk. I chose to speak about this work because, because it intersects some of the things that people in the department are interested in, coloring and graphs, and because, I learned the existence of some of these topics from our colleagues. Like Jim told me about chi-boundedness, and I learned a little bit from Sophie as well. So I thought maybe it would be good to share what it is that we did with that. So this is work that I did in collaboration with Robbie King, Robin Kothari, and Ryan Babush at Google. And at the same time, we coordinated our archive submissions. There was another work by Sitan Chen's group at Harvard, which focuses more on obtaining bounds on sample complexity, whereas you'll see that our focus kind of mixes different desiderata, including sample complexity. Okay, but I did, and this talk is, I definitely have too many slides, so I will be skipping over some. And so my goal is to make, hopefully, that you can keep, you can follow along. And so, please do ask questions during the talk, and we'll make up for it later by skipping over stuff. And I did start with I added this prologue, which is just about states, observables, and measurement in quantum mechanics, with the thought that, many people this may not be at the top of your mind. So, in classical, if you think of a classical system, like a classical computer, we can think of the state space as being, for a classical computer, certainly a finite set, for instance, bit strings of length n. On a quantum computer or in quantum mechanics, we would think of that finite set as labeling the orthonormal basis vectors of a vector space. So in our case, it would be a vector space that is 2 to the n dimensional, where every basis vector is labeled by an n-bit string. What is a state? Well, again, now we're going to think about sort of like probabilistic classical systems. So we'll think of a state as being a probability distribution over n-bit strings. So it has these, it's a function from the set of configurations to the real numbers. It has to be non-negative, and they have to sum to 1. And in quantum mechanics, we would replace that with what we would call a density matrix. So instead of being like a vector of length 2 to the n, which describes a probability distribution, now we would have a 2 to the n by 2 to the n complex matrix, which is positive semi-definite. That is the sort of analog of this positivity condition, and where the trace is 1. Okay? So actually, this kind of reduces to the classical case when the matrix is diagonal. So if the matrix is diagonal, this condition means that all the entries are non-negative real numbers, and this means that they sum to 1. Okay, so that's the special case of this. Does that make sense so far? Okay. And now what's an observable? Like, what is something we can measure? Well, if you have a probability distribution, you can think about a random variable. Okay, so that's like a function from the finite set of configurations, the real numbers, say. In the quantum case, the analog of that would be a Hermitian matrix, again, of size 2 to the n by 2 to the n. Okay? And we think of, here I've written its spectral decomposition. So these lambdas are real numbers because it's Hermitian. The eigenvalues will be real. And these would be projectors onto the eigenspaces. And when you do a measurement, classically, you would think of drawing a random variable from your probability distribution. And that would induce a distribution over the values of the random variable. So we would get some outcome for our random variable. Quantumly, it's a little bit more subtle. Ignore what's written on the slide for a second. You can choose any orthonormal basis and measure in that basis. If the basis diagonalizes your observable, then you can think of exactly this as happening, that we kind of, we get outcome lambda, the eigenvalue lambda, with probability proportional to the trace of the projector, the spectral projector, against our state row. Okay, does that make sense? So if we measure in a basis in which our observable is diagonal, we get a data point, just like in the classical case. And typically if we measure in a basis where it's not diagonal, we don't get information about that observable. And, the expected value of an observable for a probability distribution, we sum over the distribution, and we take the weighted sum of all the observable values. And quantumly, we just take the trace of rho against our Hermitian operator, the observable O. Okay, so this is kind of the dictionary between quantum states, observables, and measurements, and their classical analogs. Does it make sense? Questions about that? Okay. So, you might have heard, like this is Heisenberg, right, that you cannot simultaneously measure the position and momentum of an electron. This is the Heisenberg uncertainty principle. And that's because those operators viewed as, position and momentum, live in kind of infinite dimensional spaces, but we'll ignore that for a moment. They're observables that don't commute with one another. Okay, so they're not diagonalized in the same basis. So you can't make a measurement in which they're both diagonal. So the kind of general principle here is that if you have a set of observables, Hermitian operators in quantum mechanics, and if they pairwise commute, well, we know from linear algebra that there's a basis where they're all simultaneously diagonal. Then we can measure in that basis, and a measurement in that basis gives us a data point for each one of those observables. And we can do that. We only have to take one copy of our quantum state and measure in that basis, and we get one data point for every one of those observables. On the other hand, if we have observables that don't commute, then we don't know how to measure them. They can't be measured simultaneously in general. And so, if you had two observables that don't commute, you might have to take a copy of your state, measure this one, then prepare your state again and measure that one. Okay? And that's the kind of problem that we're going to be dealing with in this talk. Also, it's important that measurement is destructive. So like measuring this observable on this copy of the state, typically in the general case, like I can't reuse that state. So I have to make a new copy, okay? All right. So just as an example, we're still in the prologue, by the way. This is still supposed to be the warm-up, okay? So as an example, a single qubit state is a 2x2 complex density matrix, so it's positive semi-definite, trace 1. Some observables that you could imagine trying to measure on such a state. Well, the identity is not a very interesting one. The outcome's always 1. All its eigenvalues are 1. But, these Pauli matrices, X, Y, and Z, are some interesting observables for a single qubit. They are Hermitian, so they're good observables. They also square to the identity, so their eigenvalues are 1 or minus 1. And the X, Y, and Z Pauli matrices, they pairwise anti-commute. So you can only measure one of them at a time. Okay? That's single qubit Paulis. And now we can think about n qubits. Okay? So if we have an n qubit state, now we have, again, a density matrix that is 2 to the n by 2 to the n dimensional. The rows and columns are labeled by binary strings of length n. I've written the single qubit Paulis here because now I want to think about n qubit Pauli matrices. Those are just tensor products of these guys, and I take n of them in tensor product. So I'm going to omit the little tensor product symbol. So this is like n equals 2. This is the 4 by 4 identity matrix. This is X tensor identity, and so on. Okay, there's 16 of them. And given what I just told you, if we take any pairwise commuting subset like this one, so remember that X, Y, and Z pairwise anti-commute. So XX commutes with YY because XY is minus YX. And so I get minus sign twice. And so these are pairwise commuting observables. I can measure them all by measuring in the basis in which they're all diagonal. Okay, as an aside, and I will use this terminology later in the talk, this kind of measurement where I choose a set of commuting Pauli observables and then I measure in a basis that diagonalizes all of them, it's kind of a very simple kind of measurement in quantum mechanics. I'll talk more about it in a moment. It can be performed using a kind of unitary that is kind of classically simulable in a sense called a Clifford. So it's kind of a special kind of measurement that relates to a classically simulable subtheory of quantum mechanics. As a second aside, sometimes it's interesting to think about the weight of these operators. So like, this xi has only one non-identity, whereas this xx has two non-identity Pallies. So we would call this like a one local Palli, and this is a two local Palli. And in general, we might be interested in, k local Pallies. Why? Well, because if we have like a system of, if we have like a material in physics, typically, if it's, so I'll talk more about fermionic particles later, but for spins, if they interact k particles at a time, they would be described by a sum of terms, each of which is a k local Pauli. So somehow the locality here of a Pauli, can be thought of as like how many individual constituents are interacting at a time. Okay, and so we're interested in like difficulty of tasks as a function of k in some cases. Okay, so why should you care about Pauli observables? Well, if we take the full n-qubit Hilbert space and ask for a basis of all the Hermitian operators, we can always write any Hermitian operator as a sum of the 4 to the n Paulis with some real coefficients. So that's, if we care about some other observable, we can always expand it in that basis. So it's sort of useful in that sense. And it's also true that like the operators that describe the energy of systems in physics and chemistry are described by observables. And so they're often expanded as sums of Paulis with real coefficients. For a material that's like made of spins, then you would typically see k local Paulis. For something in chemistry where the individual constituents are fermions, you would have a different notion of locality that I'll talk about later in the talk. Okay, so those are two interesting subcases. You can also think, is kind of a funny thing, but you can think about, if you think about the classical case where we have a diagonal density matrix, which is a probability distribution, then if we look at the expected value of all the z-type Paulis, meaning the ones that are only tensor products of identities and z's, so those are the Fourier coefficients of the probability distribution, like the binary Fourier transform. And so you can think about the expected value of more general Paulis as some generalization of that. And that's a kind of useful perspective because, okay, this is just like philosophy, okay? Soon I'll get to what we're actually talking about. But, diagonal density matrices are the familiar classical limit where things that are probability distribution over binary strings. That's like the classical probabilistic computer. But if you take any commuting set of Paulis, it defines a kind of equivalent but different classical limit that's just as good. Because if we take the joint eigenstates of this commuting set, we get all the basis vectors of our Hilbert space, the bit strings. But if we take the joint eigenstates of any other commuting set of Paulis, those things are called stabilizer states and are also classically, fully classically simulable. And there's a kind of equivalence between maximal commuting sets of Paulis, which is unitary transformations from this Clifford set. So somehow if you like Fourier analysis, then you shouldn't just think about, z-type Paulis. You should think about any commuting set as being the right, and stabilizer formalism as being the right generalization. And this stabilizer formalism, kind of this perspective, is very important in quantum error correction, classical simulation of quantum computers, and its extension to the resource theory of magic, and so on. Okay, so that is why you should care about Pauli observables. And that's the end of the prologue. But are there any questions at this point? Yeah?
One question for the previous slide.
Sure.
Fourier coefficients on what exactly?
Of the probability distribution, yeah, as a real valued function. Okay. Okay, so what does this talk about? This talk is about strategies for learning the expected values of many observables. Okay? And, let me tell you more about what I mean specifically. So, in the classical case, so now I'm just talking about classical, this is only going to be one slide on the classical problem. We're just given samples from an unknown probability distribution. You have a black box that generates a sample and then another sample, and they're all IID from the same distribution. And we have a set of observables that we want to compute. And we want to compute all of them to within a precision epsilon, okay? So we want all of them to be within this precision epsilon with, say, probability 99%. So here's our kind of the input-output behavior. We have our samples. There's some number m of them. And we have our precision. And then we plug that into a learning protocol. It's supposed to spit out estimates for every observable in our set, such that this holds for all the observables simultaneously with probability at least 99%. Okay? And, you know, it's not a very interesting problem classically because the simple protocol is the right thing to do. You should just take some number of samples, compute the sample means of all the observables. Okay, so if I choose, how many samples do I need? How big does m need to be for this to be true? Say for a single observable. 1 over epsilon squared, right? But now, if I want it to be true for all the observables simultaneously, then I should take a little bit more, like 1 over epsilon squared times log the number of observables. That will make the probability that this happens like 1 over the number of observables. And so then the probability that happens for all of them is a constant. Okay, so the total number of samples that you need for this classical problem is just this familiar 1 over epsilon squared, and then this like log s that's not, you know, for the most part in this talk, you can ignore factors of log s, okay? So if you know, but it's just to beat down this failure probability and make it so that we get all of them all at once, okay? So then you can say, well, what about the quantum version of this problem? And, you know, you might think that there's just some like very boring name for the quantum version of this problem, but in fact there is a very non-boring name for some reason, which is shadow tomography, which was, I think Scott said that it was coined by Steve Lamia, but is that right? Yeah, anyways. So, you know, here's the quantum state, and I guess it has this shadow. I don't really know. But it's the same problem, but for quantum state. So you're given copies of an unknown quantum state, m copies, and you have a set of observables you know beforehand, and you want to estimate them all to within epsilon error. So again, we have our kind of input-output behavior. Instead of samples, now we have copies and precision, and again, we want our estimates, and we want them to satisfy that the expected value, which in quantum mechanics is trace of rho against the observable, should be close to the estimate, epsilon close for all of them. And, okay, the naive algorithm, which I didn't even mention in the classical case, the really dumb thing you can do is just fix one observable, take 1 over epsilon squared log s, estimate it to within epsilon with probability 1 minus 1 over s, and then do that for all the observables. And then you'll get this annoying factor that's linear in the number of observables because you're doing them one at a time. Does that make sense? Because this is like a very silly thing to do. And this is much worse than the classical case, right? But you see the problem, right, is that in the quantum case, because things don't commute, you know, every time you make a measurement, you can only get the observables that are diagonal in that basis. And so it might really be that you just need to measure like a linear number of times to get all the observables, okay? If they don't like, they can't be partitioned into a small number of commuting sets. Does it make sense? Okay, but it turns out that it's actually not the case. Okay, so, you know, I told you there's this subtlety, but it turns out that that linear factor can, in fact, I did already explain all these factors. The linear factor can actually be avoided in general for bounded observables, so that you do not, but, okay, so the linear factor goes away in the general case. This log will have some higher power, but we don't really care about that. And the protocol that achieves this is very complicated for general observables. It involves measurements that take chunks involving more than one copy at a time and does something jointly on all those chunks, okay? On each chunk individually and then. So the key idea is what we would call entangled measurements, like non-trivial measurements on several copies at a time, okay? And I'm not going to explain to you the general version of this that works for like any set of bounded observables, but I will explain in some way, or at least give an overview, of the version that works for Pauli observables. Okay, so actually for the rest of this talk, we're only ever going to talk about Pauli observables. So I'll now explain how this kind of linear scaling can be avoided for Pauli observables. Is that okay? All right. So this is a protocol due to Huang, Kung, and Preskill from 2021. And we're going to start with our subset S of observables. So in this case, a subset of Pauli observables. And the protocol has two stages. The first stage is really important to this talk. So I'm going to explain it at some level of detail. If you don't understand it, just ask and I'll explain more, okay? So here I've just said what this is going to achieve, and then I'll explain how it works. Okay, so the goal here is to learn the magnitudes of all the Pauli observables in the set. So remember that the Paulis, their eigenvalues are 1 or minus 1. So their expected values could be anywhere from minus 1 to 1. But in this stage, we're just going to learn the absolute value to within some epsilon error. Okay? But the claim is that you can do that extremely efficiently. Like the number, again, we're going to ignore this factor of log s, but then the number of samples, if we ignore the log s, is really just like a power of epsilon, inverse power of epsilon, which is really great. It's sort of like saying, you know, all the magnitudes somehow come from a set of commuting observables. And now I want to show you why that's true. Okay? Does that make sense as a goal? Yeah. So, right, so what we're going to do is, this is again how this key idea comes in of taking like chunks. So we're going to take 2 copies of rho now. Okay? Now, if we take 2 copies of rho, now I want to consider the set of operators that is not like, I'm going to take p tensor p for all the, well, I said p and s, so, but I could take p tensor p for all the Paulis in you know, all 4 to the n Paulis. Remember that a Pauli and another Pauli either commute or anti-commute. So p tensor p and q tensor q, when you commute them past one another, either you get 2 plus signs or you get 2 minus signs. So p tensor p and q tensor q always commute with one another. So this is a commuting set. Okay? And if I measure rho tensor rho in a basis where this is diagonal, then I get a data point for all of these that helps me estimate the trace of this against that for all of them at once. And what is that? Well, the trace of rho tensor rho against p tensor p is the trace of rho p squared. So I get a data, by measuring this special Bell basis, it's called, on 2 copies, I get a data point that helps me estimate trace of rho p squared simultaneously for every p. And so I need error epsilon to the minus 2 for the square, because I'm going to take the square root afterwards. And that requires epsilon to the minus 4 measurements. Does it make sense? So this Bell basis trick is very important. Okay, so in this first step, using this Bell basis, we get to learn the magnitudes of all the Pauli observables to within epsilon error. And now there's this kind of crucial observation, which is that from this data, we can already figure out which are the ones we don't care about. Because it could be that like some of these expected values are actually just like to within epsilon error well approximated by 0. Like it could be that our estimate tells us that, you know, this is just, you know, yeah, I mean, if we estimate that this is like epsilon over 4, then we can just output 0 as our estimate for that Pauli and not worry about the sign. And for the other ones, the ones where the magnitude is at least epsilon, those ones we need to figure out what the sign is in order to output our expected value, our estimate. So that's the crucial thing, is like we learn the magnitudes and then we throw out all the ones that have small expected value where we can just output 0 as their expected value. And then we focus on these ones, the set S epsilon, which is like a thresholded set. Okay? And then there's a second stage, which I'm not going to explain because it's not important for this talk, but there's a second stage where you entangle many more copies at a time. In this stage, epsilon to the minus 2 log s, or performing a big measurement on that many copies at a time. And from that, we learn the signs of all the Paulis in this set that we have focused on. Okay, so the learning the signs is like the tricky part. Okay. But, you know, okay, so I hope this gives you an idea of how, you know, you can learn many non-commuting observables by doing entangled measurements on a few copies at a time. In this case, at most this many copies at a time. And this protocol is in some ways almost the best we could hope for this problem of Pauli shadow tomography. Because, think about, okay, so what is the number of copies of the state we need? Well, it's an inverse power of epsilon. It's epsilon to the minus 4. You know, you could ask whether or not that's optimal. It's an interesting question. But it's logarithmic in the size of S, and that's like really great. The runtime is also polynomial in the number of observables, number of qubits, and inverse error, so that's the best we could hope for. And the number of copies per measurement, this thing is kind of big, right? It's like growing with epsilon, which is maybe not ideal, and that's kind of the purpose of this talk, is to say, like, can we get away with fewer copies per measurement? Okay, so that's kind of the problem that we want to look at. Okay. So this is what that's why we gave it this name, triply efficient. So then you're triply efficient if you're sample efficient, meaning you can get polynomial in log the size of S, so you don't have this bad linear scaling with the number of observables and 1 over epsilon. You should have a good runtime. And we want the algorithm, this is the key thing that differs from HKP. We want the algorithm to only use joint measurements on a very small number of copies at a time, like 1 or 2. Okay, like say a constant independent of epsilon, the size of S, and N. And you might say, is this possible at all for interesting sets of Pallies? Okay? And it is known to be, before our work, it's known to be achievable in certain special cases. And there's a very significant special case, which I want to tell you about now. Okay? And this is a very simple and beautiful protocol, which was, it's often attributed to this paper, but it was present in many other papers around the same time, and also I think was folklore before that. Okay, this is the task where S, the set of Pallies we want to learn, is the set of k local Pallies for a constant k. Okay, so we want to learn, tensor products of I, X, Y, and Z, where the number of non-identity things is at most k, and k is a constant. Okay, so there's roughly, 3 to the k, and choose k of them. Okay? Okay, so how do we do that? So here's the protocol. We're going to take one copy of rho, and we're going to look at the qubits of rho, and we're going to choose a single qubit basis, x, y, or z, for every qubit of rho. So if rho is a 6-qubit state, we choose x with probability a third, y with probability a third, and z with probability a third for each qubit. So we randomly choose a string like this. And now we're going to measure in a basis where you have to be consistent with each one of these, okay? So if your Pauli says x here, you're getting a data point, or if it says I here, you're getting a data point, right? It has to be consistent with every one of the Paulis that you chose, okay? There's a basis that's consistent with all of those, and that's the measurement we're going to do. So you can say, like, what is the probability if we have a k local Pauli, like say k is 2, and we have xx? What's the probability that it's diagonal in this basis that we chose? Well, for each position where the Pauli is non-trivial, we have a 1/3 probability that we chose the basis consistent with it. So a k local Pauli is diagonal in this randomly chosen basis with probability 1 over 3 to the k. And what that means is that for the k local Paulis, we need roughly, this is sort of the probability that for any given Pauli, we get a data point every time we measure. So we need this, the inverse of this, times epsilon to the minus 2 times log s sample, because we want 1 over epsilon squared log s data points for each Pauli in our set. Does that make sense? Okay. So this protocol only involves a single copy of rho at a time. In fact, we're just making single qubit measurements, which is even better. And it's also time efficient and, like I said, uses single copy measurements. So this is what we would call a triply efficient protocol for the set of k local Paulis, which is great because k local Paulis like appear in lots of locally interacting systems, like a magnet or stuff like that. Okay? Other questions or comments? Okay. Yeah, go ahead.
What's the typical value of k that you consider?
Well, k equals 2 is the most physical, right? Because most systems interact with two particles at a time. Okay. But I want to now talk just more broadly about how to think about single copy learning protocols like this. So and the connection with coloring, okay, which I promised at the beginning. So let's consider a set of Pauli observables S. And, you know, like I said, every Pauli every pair of Paulis either commute or anti-commute. So for our set, we can write down a graph which has a vertex for every observable, every Pauli in the set S, and has an edge whenever they anti-commute, okay? So we call that the commutation graph, even though the edges are when they anti-commute, okay? So it's a little confusing. So here's an example. These are some 2-qubit Paulis, and, you know, XX and YY commute, so there's no edge, but like XX and IY anti-commute, so there's an edge, okay? This is an example of a commutation graph. And shadow tomography protocol is based on single copy Clifford measurements, measurements where we just choose a commuting set and measure in a basis diagonal with that set. They correspond to colorings of this graph, okay? That's very easy to see. Like, for instance, here's the same graph. Here's a coloring, right? So remember our coloring, vertex coloring, the colors of, you know, all the vertices of a given color have to be an independent set. That means they commute with one another. And so we can measure them at the same time. So this gives us a schedule of Clifford measurements. First, we measure one copy in the basis that diagonalizes the purple ones. Then we measure another copy in the basis that diagonalizes the orange ones, then the green ones, and the blue ones. And so if we have a coloring of this commutation graph with chi colors, this gives us a deterministic partition into chi commuting sets of Paulis, and then we can measure each of them in a Clifford basis. So the cost of this strategy is like chi times 1 over epsilon squared times this log S factor, okay? But actually, you may, if you're paying attention, notice that this does not quite describe protocols like the ones that I just described for k-local Paulis. Does anyone see why? It's almost, but not quite. Maybe it's highlighted on the slide somewhere. So, yeah.
For k-local Paulis, it was a random.
Yeah, so this is deterministic, whereas that strategy was randomized, right? So actually, the correct thing to describe randomized strategies like that is the fractional coloring, okay? So a fractional coloring of a graph with chi colors is a probability distribution over independent sets, such that if we draw an independent set from that distribution, then the probability that a fixed Pauli is in the independent set is at least 1 over chi. Because this is a relaxation of the notion of coloring. And you can just think of it as like some randomized relaxation of coloring. And this is, this formula is saying that if we measure in the Clifford basis corresponding to I, we get a data point for a given Pauli with probability at least 1 over chi. And that's the way that the k-local Pauli's algorithm works. So, right, so this corresponds, you know, it's another way of describing a randomized schedule of Clifford measurements that learns all the Paulis. Okay? So, for k-local Pauli observables, there is already this triply efficient shadow tomography scheme, and it's based on single copy Clifford measurements, which you can also think of as fractional colorings of this commutation graph. Okay?
So did you already say why it's triply efficient?
Oh, yeah, because it achieves a number of measurements that is like, or a number of copies that is like polynomial in 1 over epsilon and log the number of observables. And the runtime is polynomial in n and 1 over epsilon and the number of observables. And it only uses 1 copy at a time. Does that make sense? So we avoid that linear overhead in the number of observables. That's why it's a good shadow tomography thing. But then also achieving time efficiency and a small number of copies per measurement makes it triply efficient. Okay. Right, so in this work we give these kind of triply efficient protocols for other sets of Pauli observables. So let me just tell you what those are. So those are the k-body fermionic operators and the set of all Pauli operators. Now you might say, well, that sounds way better than that. Why don't we just do this and then forget about everything else? But the definition that we use is that you're allowed to use a runtime that is linear in the number of observables. And the reason for that is because at the end you have to output all the expected values for every observable. So when we talk about all Pauli operators, we're allowed a runtime that is like linear in 4 to the n, or sorry, polynomial in 4 to the n. because we're at the end outputting all the Pauli observable. So this gives us a much bigger runtime budget. So this does not imply that, or a triply efficient protocol for a larger set does not imply one for a smaller set. I want to tell you what a k-body fermionic operator is. It is also described as measuring a set of Pauli operators, and if you've never seen this before, and if you're a computer scientist, you should, I would advocate that you should know what this notion of locality is, because the bitwise locality that we talk about in computer science that appears in like sum of squares hierarchy and things like that, that is kind of the notion of locality that is like k-local Paulis. It's the same bitwise notion of locality. But there's another notion of locality that is relevant in physics and chemistry, and is another way of kind of grading like the set of all the Paulis. And in many ways, it is more general and more natural. So here's how it works. You fix a specific set of 2n pairwise anti-commuting Pauli operators. So I say specific, like I mean you fix it. So you can take any set, but then you have to fix it. So these are pairwise anti-commuting. And then you take all the words of weight 2k in those anti. So this is like a clique in this big commutation graph. And then you take products of 2k of these elements at a time. That's the set of k-body fermionic observables. And so when k is 2, you'd get an operator like this, where the q's are pairwise anti-commuting Paulis. These Hamiltonians that describe interactions between electrons in molecules are described as sums of operators like this. Okay? So learning them is interesting for quantum chemistry. All right. Questions about that? Okay. Yeah, maybe I'll say one more thing about this, because I'll say one more thing about this. So when you have like a bitwise locality, the smallest locality that's interesting is one local, okay? And one local, like a one local cost function is like easy to optimize because there's no interaction. So everybody you optimize every bit individually, okay? I'm not saying anything complicated. The kind of simplest, if you think about this version of locality, the simplest case is when k is 1. And that corresponds to quadratic operators in these pairwise anti-commuting variables. And those cost functions that are quadratic in those pairwise anti-commuting variables, they're Hermitian operators, the sum of pairwise of quadratics. And those describe free fermion systems. And there's a kind of rich family of classically simulable transformations that map those to non-interacting, but they're not the same. And so it's kind of an interesting generalization of the non-interacting case. Okay. Okay, so what is interesting about these observables, the ones we handle in this work? Unlike the k-local Paulis, it's actually impossible to achieve even sample efficiency alone using single copy measurements. So you need to use 2 or more copy measurements to achieve even just one of our desiderata. Okay, and that was proven in these works for the two things. And our protocols, use not single copy measurements, but 2 copy measurements and achieve this. I'm going to skip this. You've already sort of seen why 2 copy measurements, because this Bell sampling trick is very powerful. And I'll tell you an interesting framework for learning with 2 copy measurements that relates to other graph coloring problems. And then I'll tell you about one of our results, and then I'll wrap up, okay? So what is the framework? So we're going to consider a set of Pauli observables S. I should say that this framework was really not due to us. It's proposed as a heuristic algorithm in this paper. And our contribution is to make it, like to prove a performance guarantee for this in the context of the things that we care about. So again, we're going to use Bell measurements. So we're going to learn all the magnitudes to within epsilon area using a very small number of measurements. And that's going to help us learn which ones we can throw out or approximate by 0 and which ones we need to figure out the sign of. And then in the second stage, you remember this other algorithm had this complicated multi-copy measurement. But now what we're going to do is we're just going to use single copy measurements to learn all the ones in the set that we care about. So we winnow down the set to this set S epsilon that's thresholded by epsilon. And now we just need to learn the expected values of the Pauli's in that set. And the hope is that that is easier than learning them all. So here's an example. We have our set of 2 copy Pauli's, and we have our m copies of rho and our epsilon. We're going to do 2 copy Bell measurements. And then that's going to give us some smaller set. That this set S epsilon, it depends on epsilon because it's thresholded. And it also depends on our unknown state. So its dependence on rho is kind of a little bit mysterious, right? But now we just need to learn the expected values of these observables. And the question is that actually an easier task, like asymptotically or in the worst case? Because it's like crucial that that's true for anything we're doing to be useful. So like, just again thinking about the commutation graph, we start with a set of observables. They have some graph. After we do the 2 copy Bell measurements, we throw away all the vertices of this graph that correspond to Pauli's whose magnitude is too small. And then we get some winnowed down graph, sparsified graph. And that's the commutation graph of this set S epsilon that's thresholded by epsilon. And the second step is to do single copy Clifford learning on this graph, which means compute a fractional coloring of this graph with small size. Okay? And the sample complexity, I mean, it doesn't really matter, but the point is that if chi is small, then we're happy, okay? Like there's this dependence on epsilon that's totally fine, and log s that we said we were going to ignore, and basically what we need to worry about is chi, the fractional coloring number. And we already said that like there are sets that we care about, like the k-body fermionic observables, where if we just took the chi of this graph, this would scale polynomially in the size of s, so this would be very bad. And so what we're hoping is that when we go over here, we can do a lot better, like exponentially better in the size of s. And this is an aside, because all the measurements are from this special Clifford set, this protocol can also be viewed as learning a classical compressed representation of the state, which is a kind of interesting related task. Okay, so this framework, as I said, is only useful if we can compute good fractional colorings or colorings of this commutation graph. And it's not just good, it has to be like vastly better than the colorings of the graph before we winnow it down using Bell sampling. Okay, it has to be like exponentially better. And you might ask how we can do this. Okay, so that is, I was rock climbing with Jim, and I asked him, how do you bound the chromatic number in terms of the clique number? And he told me about this area of chi boundedness, and it turns out that that is quite useful to us. So basically, the thing is, like I said, that this S epsilon thing, the winnowed down set, it depends in a complicated way on the state rho, in a way that we really don't understand or have much control over. And I only know how to prove 2 properties of it. One is that the largest clique in this graph has size at most 1 over epsilon squared. And the other one is that it's obtained from the original graph by removing vertices. And those are the only 2 properties that I know. Okay, so how do you prove this? It's very easy to prove, but very hard to generalize this proof. Okay, so I think that like the true direction for making further progress in this area is to find a better version of this kind of uncertainty relation that's used in this proof. Anyways, the way this proof goes is that if you have a clique in this graph, it's a set of pairwise anti-commuting Pauli's. And because they're in the set S epsilon, their magnitudes in a quantum state rho are at least epsilon, just by definition. And it's just a fact that it's not hard to prove that for any anti-commuting observables and any state rho, the sum of the squares of the expected values is at most 1. Okay, this is what we call some kind of uncertainty relation. For those of you that work in quantum computing, this is a generalization of the block sphere constraint, that quantum states live in the block sphere, like the trace of rho against x all squared plus y all squared plus z all squared is at most 1. Okay, but this is not hard to prove. And then because we know that the magnitudes are at least epsilon, we can lower bound that by epsilon squared times the size, which is t. And this tells us that t is at most 1 over epsilon squared, so that's the size of the clique. Okay, so this is the whole reason why the cliques in this graph are not big. On its own, this isn't enough to guarantee a good coloring because there are graphs which have, their largest clique is of size 3 and they don't, the number of colors needed to color them is like the square root of the number of vertices. So this is not good enough. But we can also use the fact that we got this graph by taking the commutation graph of our set of observables and removing vertices. So it's an induced subgraph of this. And so we want to use these two properties together to get a bound on the chromatic number in terms of the clique number. And that is this idea of chi-boundedness, which is to say that like we want to show that the family of induced subgraphs of our commutation graph has an upper bound on chromatic number in terms of clique number. Okay, that's what we want to do. Because we know that ultimately we're going to be working with an induced subgraph, and we know its clique number is at most 1 over epsilon squared. Okay, so, right, so I was going to give some examples. I think, yeah, okay, so an example of a family of graphs that is chi-bounded is graphs whose longest induced path contains at most L vertices. An induced path is a path that contains all edges with both endpoints in the path. Okay, so like this green one is an induced path. So the family of all graphs with longest induced path at most L, you can prove the following upper bound on chromatic number in terms of clique number. And this can also be made algorithmic. And we do that in our paper, although I think it's,
Sorry,
yeah.
didn't quite understand what it means for both endpoints of an edge.
Oh, so like suppose you had an edge between this vertex and that vertex, then it would not be an induced path.
Ah, I see.
Yeah. Does that make sense? Okay. All right, so I was just going to give, this actually doesn't really lead to any of our best results, but just as an example, it turns out that like any commutation graph does not have long induced paths. Like this is a graph, like the set of all Paulis with 4 to the n vertices. It's a, but the longest induced path is actually only of size 2n plus 1. Okay, so how do you prove that? Well, okay, so what you do is you take the vertices of an induced path and they satisfy some commutation relations. Like they have to commute if they're more than one apart in the path, and then they have to anti-commute if they're nearest neighbors. And from these commutation relations, you can construct products like P1, P2, P1, P2, P3, etc. And you find using these commutation relations that come from the fact that they form an induced path, that these all are pairwise anti-commuting. Okay? And do you know how many pairwise anti-commuting operators you can have in an n-qubit Hilbert space? You can't have more than 2n plus 1. That's this thing about Clifford algebras or, So because you can't have more than 2n plus 1 pairwise anti-commuting operators, L cannot be greater than 2n plus 1. So it turns out that like any commutation graph of Pauli's can't have an induced path of more than 2n plus 1 vertices, even though the graph has 4 to the n vertices. Like I said, this does not lead to like any of our best results, but it does give some, it gives a kind of interesting implication that has to do with, so you can use this to say that, if we were to try to learn all the Pauli's, then we can do this protocol that I described using Bell sampling and then fractional coloring, and we would reduce to a fractional coloring problem in this G of S epsilon, which has the largest clique of size 1 over epsilon squared, and therefore we can do the second stage in a time that is like, or number of copies that's 2n plus 1 to the power of 1 over epsilon squared. So this is not, it's kind of interesting, and when epsilon is a constant, it's already a little bit interesting. But this is not the best we can do, so I only included this as an example of the strategy. The more interesting thing is the case of, I want to skip over that. Fermionic local observables, which I'll end with. So fermionic local observables, we do get this kind of upper bound on it actually, in our case, is it really is a fractional coloring in our case. And it's an upper bound on fractional chromatic number in terms of the clique number for any induced subgraph of the commutation graph of k-body fermionic observables. And this upper bound is some polynomial that depends on k, where k is the coloring, the like k-body fermionic observable. So we think of k as being a constant, like 2 or 4 or 3. And yeah, this leads to, okay, so that's our theorem. I'm not going to describe the proof. But if we apply this and use our strategy, we get a triply efficient shadow tomography protocol for k-body fermionic observables. And the sample complexity is now this polynomial p that depends on k of 1 over epsilon squared times log n. So the dependence on n, the number of fermionic modes or qubits, is logarithmic. Whereas any protocol that uses single copy measurements actually has to use a polynomial number of copies in n. So this is an exponential improvement as a function of the number of qubits. And you might be suspicious of the fact that I did not specify what the dependence on k is. And that would be appropriate. In our work, the scaling was very bad. Like it was omega to the 2k to the k plus 1. But then Janzer-Jin, Sudakov, and Wu improved it to linear, like the omega to the 2k plus 1. So, and so that's very nice. Okay. That's basically the end of my talk. The summary is that these shadow tomography protocols with single copy Clifford measurements, you should think of as fractional colorings of this commutation graph. And if you can do a little bit better and understand how to color the family of induced subgraphs using a number of colors that depends in some mild way on the clique number, so if you can establish this kind of copy-boundedness result, then you get shadow tomography protocol with 2 copy Clifford measurements. And here you can do, in some cases, exponentially better than here. So that's it. And I did want to say one other thing, which is that I think to go further, it's not a graph theory problem. I think that the right way to go further with these results and to understand, because what we don't solve is like, for a general set of Pauli observables, can you do this triply efficient shadow tomography? And I think to go further, you have to understand the kind of uncertainty relations that hold for all quantum states. So like in the proof of this clique thing, we use this fact that if you have pairwise anti-commuting Paulis, the sum of the squares of their expected values is at most 1. Now you could try to just, this is like a sum over a clique. You could try to replace this with a sum over a fractional clique. So a fractional clique is now a probability distribution over all the Paulis, or not a, sorry, a real valued function over the Paulis that satisfies some constraints, and you would just put that function sitting here and sum over all Paulis. And it's no longer true that it's bounded by 1, actually. There are counterexamples. But you might say, well, maybe it's upper bounded by 2, and I don't know a counterexample to that. And so, like, I think understanding these kinds of uncertainty relations that have to do with Pauli expected values is something that is worthwhile and would inform further progress in this area. All right, thanks.
Questions?
Thank you very much for the talk. I'm not expert on quantum computing or such things, but I'm very interested in applications of Clifford algebras. Is there any application of Clifford algebras inside what you do? I saw Clifford names, Pauli
if you like
things.
Clifford algebras, then really what you're talking about is fermions, because the k-body fermionic observables, we start with a set of Paulis, C1, C2 up to C2n, that are Ci, Cj plus Cj, Ci is twice delta Ij. So we start with the Clifford algebra. And these would be like, so these are, would be called Majorana fermion operators. And then the weight, k-body fermion operators are just, monomials of weight 2k in these elementary Majorana fermion operators. So, Clifford and the thing is that that grading of Paulis by fermionic locality as opposed to bit locality As I said, like at the lowest level, you have this like theory of free fermions, which is another subtheory of quantum mechanics that is fully classically simulable, just like stabilizer formalism. And actually, stabilizer formalism and this one are basically like the only, well, in some ways, the only really rich classical subtheories, efficiently simulable subtheories of quantum mechanics. So I think that Clifford algebras, fermions, they go together, yeah.
And computationally, one of the best things that we can do with Clifford algebras is that it's free of the representation. It's free of coordinate free, so you can do the calculations and then choose a basis. And it's good when you have lots of products.
Do you mean
and
by
things.
transforming, like taking a linear combination of the original C's? And
Yeah, when you
Yeah, so that
when
would
you
be
have things
called,
on different frames and
Yeah, so I think what you're talking about is fermionic linear optics, or like fermionic Gaussian unitaries. And that's like the classically simulable subtheory that I'm talking about. I think maybe it's the same thing.
excellent. Thank you very much.
Other questions? So I missed the significance of this inequality that you showed at the last.
Oh yeah, well that comes into this proof that if I have a clique in a commutation graph, which is, okay, so it comes into this proof that once I've winnowed down my set of observables to the ones whose magnitude is at least epsilon in a given state, then I can prove that the largest clique, the largest anti-commuting set in that subset has to be of size at most 1 over epsilon squared. And the way you prove that is using that inequality, because we have that inequality, it just sits here. That comes from the clique. And then I use the fact that all the observables have to have epsilon expected value, and so this is lower bound by epsilon squared times t. And then I rearrange and I get t is at most 1 over epsilon squared. So that's where it comes in.
Yeah.
If you could generalize this to largest fractional clique, then that would give a vast simplification and improvement of our results, and make the strategy based on chi-boundedness kind of, old news. Like you could do something much more powerful if you could prove a version of this lemma with fractional clique replacing clique. Yep.
Thanks, David. Oh, you have a question? Sorry.
Sure.
Thanks for the talk. This is a bit of a vague question, but do your results have any implications for physics in the sense that, let's say, one of our colleagues in the physics department who is not in the computing domain would be interested? And
So I can tell you that, one of the plans for quantum computing is to do quantum chemistry. Like that is kind of, most of the industrial groups are planning to do some quantum chemistry type algorithms. And in the course of those algorithms, it is actually important to measure the energy of, a molecule, or typically a molecule in those algorithms, in a given state that is prepared by the quantum computer. And so they are interested in strategies for doing that. And there was a question when we came up with this of whether or not this would be useful. My guess is that it's probably not like the thing they're going to do, but it's close. It sort of touches upon similar things and is motivated by that. And you could imagine scenarios where, we haven't revisited it since the Sudakov thing. I mean, basically k equals 2 is the interesting case for chemistry. And my guess is that the overheads of this are probably not worth it, but it's not so far off from what people want to do. Yeah.
thanks.
So, one more.
So we might have missed it earlier, but you said you had a slide where you had a bound involving epsilon to the -4, and you mentioned something about that not being super relevant or like removable in some sense. Like, why was that the case? It also
No, I said you might ask whether or not it's optimal.
I see.
I think I said that. So people have asked whether or not it's optimal, and I think there are some partial results along that line. Like, I don't think there's an unequivocal statement, but there's partial results. So in some sense, epsilon to the minus 4 is required, but I don't even remember which sense it is.
I see. Also, what generally are the precisions epsilon that tend
Well,
to come up?
that's yeah, probably. Yeah, that's a very good question. I mean, in chemistry, I think that the precision you would want, because you're going to be summing a bunch of these terms, so the precision you want is inverse polynomial n, which now makes this not a very good thing to do if you have epsilon to the minus 4. So, you know, I think you're right to ask that. Like if you care about like a sum and you want, you know, the sum to be inverse polynomially reproduced, then there might be better things that you can do. But if you only care about like extensive error, so like, you know, the sum to be within some approximation ratio of the true value, then you could take epsilon to be a constant, say, or something like that. Yeah.
I see. Thank you.
Okay, thanks again to David and to you for all the questions.